speed up convergence on image data, this paper introduces the correlation alternative to batch normalization. So today I'm reading a paper called Network Deconvolution from Evanusa, Mitrokhin, Goldstein, Yorke, Fermuller, Aloimonos from Department of Computer Science, University of Maryland, College Park. So in this paper, they observed that there are strong correlations in the real-world image data, and what they want to do is to remove pixel-wise and channel-wise, that is cross-color correlation. And by doing this, they want to compete with batch normalization, and they claim that on popular datasets they actually achieve faster convergence or longer convergence with better results. They have also a biological explanation for this method, and that is that they observe that in nature there's this center surround structure in biological neurons in the visual brain, which actually looks for edges in the picture in a way. So it looks specifically, it looks for so it activates, those neurons activate more when there's some some big change, when you have this big activation on center pixel, but the pixels around that are not activated. So in that case, there's it's bigger activation than if you have sort of activation across the center one and the surrounding one. Okay. So they mentioned they have this, so they observed this correlation, right? It's actually, I think it's well known. And what they do to decorrelate is they do deconvolution. So as an example of deconvolution, they have this picture of a horse, where if you convolve the picture of a horse with the Gaussian kernel, then you essentially get a blur of that image. And this transformation is reversible, right? Because in the frequency domain, the convolution operation is just a multiplication, and multiplication is reversible. So you can do that back as long as you know the kernel, and this is sometimes used in image processing to sort of reduce blur, motion blur, and so on. It's possible sort of to improve images with this. So they ask, in this case, what if you have the original image and you want to deconvolve that? What would be the picture of this? And of course, they show that the result of this is showing, rapid changes or some sort of edges, areas of large edges in the picture. And because you remove the correlations, you will get sparser representation, and yes, then of course you will get better performance on that. But the decorrelation itself, the deconvolution, it's a more expensive operation, and you have to sort of do it faster with some approximation methods and so on. So contributions of this paper are following. They introduced network deconvolution and decorrelation method to remove both pixel-wise and channel-wise correlation at each layer of the network. Their experiments show that deconvolution can replace batch normalization as a generic procedure in variety of domain neural network architectures with better model training. So then they have this proof of sort of optimality in L2 optimization. I will go a little bit into that, and then they also mentioned that the deconvolution was incorrectly, this term was incorrectly used in the previous papers, and they actually do use the original meaning of the deconvolution. Then of course they mention here that they, if you do the deconvolution, you will get sparser representation. They propose implicit yeah, they propose this speed up on the convolution procedure, because without it it's sort of useless method, because you would get so much loss of performance. Then they demonstrated the network, yeah, then they demonstrate the improved performance. Okay, so the operation they do is sometimes also called whitening deconvolution. And so firstly, there is this, they have this section on motivation for this approach. So say we have this linear operation, right? You have some weight matrix, you have some input, you have some inputs, matrix of inputs, and you would like to do gradient descent. So in here they say that if the input data has certain condition, it behaves in certain way, then you will converge in single step, and you will get this convergence if actually the condition is that transformed transposed matrix of data multiplied with the data matrix divided by number of dimensions, I think, divided by n, if this equals unit matrix. And it's sort of easy to show, and from this they actually observe that this condition of unit of this multiplication with transpose matrix with the matrix itself divided by n equals to 1, that this condition is actually claim on decorrelation, a claim on unit covariance of the input data. So how they actually claim this? So they have this, they have this input matrix, and they say, okay, each row is a random sample, and then you have many rows, and then you look at the covariance matrix of each. No, it's not random sample. Each row is a random variable, and then you look at the covariance matrix of these random variables, and if it's 1, then you have this special condition satisfied. And if you have this condition satisfied, then you will get faster convergence. And indeed, they observe some faster convergence if they manage to do this, to ensure this condition, change the basis of the input values in a smart way. So, they have this idea of the convolution, and they perform the convolution on each of the layers. But is there more intuitive way how to describe this deconvolution? So they have this very nice picture here, where they describe the convolution as in this nice diagrammatic way as a matrix multiplication. So they have this sliding window, right? Each sliding window, if it's flattened and added as a column into a matrix, then convolution operation becomes just a multiplication of this matrix with the weight matrix, and then you get the resulting vector. And what they propose is change basis in between the multiplication of the matrix and the weight matrix, the input data and weight matrix. So in between they add this change of the basis, which introduces this decorrelation, this deconvolution, and thanks to that they will get sparse representation and faster convergence for the price of having to actually compute this this operation. Okay, so so how do they actually how do they do this? So So this change of the basis is actually a covariance. So the change of the basis matrix, they show, it's not hard to see, is actually covariance matrix as described previously, but it's square root of it. It's minus square root of it. How to describe it? Covariance matrix to the power of minus 1/2. And of course, this is something that you do for during training, but after training, they freeze this deconvolution matrix to be running average. And then, of course, they need to do that to have faster prediction. They have this section on how to calculate the inverse square root of the covariance matrix in a fast way, approximately, and they describe it here. I'm not going to go through it. Then they have this interesting picture showing how the deconvolution actually looks on the picture of the horse. So it's very hard to see, but actually after the convolution you will see only edges of the horse, sort of the outline of the horse shape, and that that highlights the sparsity result. They have these nice graphs where they show the faster convergence on Fashion-MNIST compared to the batch norm. So they have this one model when they do initially they do batch norm, and then they have this another network where they do in each layer they do their decorrelation. They show that they converge faster. They have also this table that they are able to achieve faster. They are able to achieve few percent better performance, but more importantly, they can get there faster in wall clock time, and that's actually without some additional performance improvements, for example, calculating this inverse square root on GPU. In the appendix, they have this figure 12 where they show the accuracy versus wall time, and they show here that they converge always faster to the better result, but they're sort of higher. It's a graph of accuracy compared to wall time, and of course, when you want higher accuracy or higher wall time, the difference of the deconvolution compared to SGD becomes smaller. But if you want sort of low accuracy, then you can get there faster. So that's all from this paper. I hope you got your spice of this paper. Please dislike, unsubscribe, and let me know how bad the video is in the comments. And yeah, if you have any suggestions, let me know, and I hope to see you next time. Bye.